this screencast, I will show how to calculate the Fourier series expansion of a piecewise defined function, which is this function here. Now, this function, first of all, has period 2 pi. That's how it is constructed. So, period 2 pi. And we also note that since we're dealing with a piecewise defined function, that the definition of the function changes over the period. Definition changes over the period. So let's get on with it. The definition of the Fourier series is down here. So f will be represented by this, and what we need to find is a0, an, and bn, and that's it. So the definitions for an and bn are here. Let's start with a0. Now a0, we could use this definition, is 1 over pi. We need the integral from 0 to 2 pi. And then we've got f of t cos nt dt, but because we're looking at a0, n is equal to 0, that means we've actually got cos of 0, which is 1. So I might as well already replace that to make this integral simpler. Now, to integrate this, first of all, let's check. We've got the limits here from 0 to 2 pi for the integral. The definition of our function here is from negative pi to pi and then repeating. So we would be fine using 0 to 2 pi, but we would have to think about what we have between pi and 2 pi. So a simpler way of doing this is to change the limits for the integral. We are integrating over a whole period, and that means it doesn't really actually matter where we start, as long as we integrate over the whole period. So we can go from 0 to 2 pi or from negative pi to pi, because it's still over the distance of 2 pi. So by doing this, I can just quickly put in what the two different functions are, because we have to split up this integral, of course. It's no longer just, it's not just one function, it is it's got two parts to it. So if we start with the integral from negative pi to 0, over this range, the function is negative 1, so we get negative 1 dt. And then we add the integral from 0 to pi, which of course has the definition, f has the definition 3, so it's integral 3 dt. And if we then calculate this, we get 1 over pi times, well, antiderivative of minus 1 is minus t, and the limits are negative pi to 0. And the antiderivative of 3 is 3t from 0 to pi. And that's 1 over pi times, well, what do we get here? If we sub in 0, we get 0. So that means we've got minus, sub in minus pi, minus is plus. So what remains here is minus pi. And we've got, we sub in pi, 3 pi. If we sub in 0, we get 0. So this is it. We actually get 2 pi over pi, which is 2. So a0 is equal to 2. Just creating a bit of space here so I can continue my calculations, but you might want to go back if you wanted to follow this step by step again. Now let's look at an. An, down there, for n not equal to 0, is 1 over pi, integral from 0 to 2 pi, f of t cos nt dt. So the same as before, I'm going to change the limits for the integral, and for the same reason as before, I'm allowed to do this. F of t cos nt dt. And again, I will need to split this up into two integrals, because the function has got different definition for those two sections we've got here. So from negative pi to 0, again I've got minus 1, so that gives me minus cos nt dt. And I've got the integral from 0 to pi, and for that I've got 3 cos nt dt. So that's 1 over pi times. Let's look at this. This is simply the integral over the cos nt, negative cos nt. So, well, that's not that difficult. The antiderivative is going to be negative sine nt, but we have to compensate for that n. So it is negative 1 over n sine nt. The limits are negative pi to 0. And for the second integral, we've got 3 cos nt, so I might as well take the 3 outside. Cos nt then becomes, the antiderivative of this is then 1 over n sine nt, and the limits from 0 to pi. Now let's evaluate this. We get 1 over pi. If I sub in 0, I get minus 1 over n. This is actually sine 0n, so sine 0. Minus, subbing in negative pi. This is a plus, because there was a minus already. 1 over n sine negative n pi. Plus 3 times, well, sub in pi. Well, let's do this step by step. 1 over n sine n pi, and then minus, well, so if I sub in 0, 1 over n sine 0, and closing all these brackets. Now, as it turns out, we can simplify this significantly. Sine of 0 is 0, so this whole thing disappears. There's another sine of 0 here. Now, what is sine of negative n pi? Okay, if we look at what n actually is, n could be 1, for example. So if n is 1, we get sine of negative pi. Now, sine of negative pi is 0 if n is 2. What do we get? We get sine of negative 2 pi. Well, that is 0 again. And if we keep doing this, you'll see that these are all 0. And that means that this disappears and is gone, and what's left is sine n pi. But for the same reason that sine of negative n pi is 0, sine of n pi is also 0, because we keep looking at similar angles. So, for example, if n is equal to 1, we have sine pi, which is 0. If n is equal to 2, we get sine 2 pi, which is equal to 0. So that means this also disappears, and overall we end up with 0. Now, this might be surprising if you've never calculated Fourier series before, but as we will see later on, there's something special about this particular function we started with, and that is that it is nearly an odd function. And if we've got functions that are nearly odd functions, then the ANs are simply 0. But it's a bit early for this. We just note this for the moment. Okay, so we'll now look at the BNs, and I might just start writing up here because I need a bit more space for this. The formula is below, 1 over pi. Now I might as well straight away change my limits for the integral. F of t, and then we've got a sine nt dt. This, of course, again is going to be split up into 2 integrals, the one from negative pi to 0 over negative sine nt dt, and the other one from 0 to pi over 3 sine nt dt. Now this is 1 over pi times, well, let's find the antiderivative. The antiderivative of sine nt is 1 over n cos nt, but with a minus in front of it. We already have a minus, so this is going to be a plus, so we get 1 over n cos nt, and the limits are negative pi to 0, plus, similar reasons, we have, well, might as well take the 3 outside, we get a minus 1 over n cos nt, the limits are 0 to pi, 1 over pi times, let's sub in 0. I might as well once again write this down step by step, and we'll simplify in the next step. So this is going to be cos of 0 minus 1 over n cos of minus n pi. That was the first lot, and the second lot is plus 3 times minus 1 over n cos n pi, we sub in pi, and then minus or plus 1 over n cos 0. Okay, so what have we got here? Cos 0 is 1. As it turns out, cos minus n pi, well, let's have a look what it is. If n is equal to 1, we get cos minus pi, and that happens to be negative 1. If n is 2, we get cos negative 2 pi, and that happens to be 1. If n is 3, we get cos negative 3 pi, and that's negative 1 again, and so on. So what we actually have here is that cos minus pi n, or minus n pi, is equal to negative 1 to the power of n. So I will make a note of this. This thing is going to be minus 1 to the power of n. Now we've also got cos n pi here, and as it turns out, that is also minus 1 to the power of n. And of course we've got another cos of 0, which is 1. So let me tidy this up to simplify in a moment. So what we get out of this is the following. We get 1 over pi. What's left here is, there's a 1 here, so we get 1 over n. Then in the next step we've got minus 1 over n, and this cos was simply negative 1 to the power of n. And then we've got a plus. What's this? This is 3 times negative 1 over n times negative 1 over n to the power of n. So I might as well do this in 2 steps. Minus 1 to the power of n, and then plus 1 over n in here, and closing this bracket as well. So let's simplify this further. We get 1 over pi, and inside the brackets we've got 1 over n, and there's another 1 over n, but it's multiplied by 3, so this gives us 4 over n. And here we've got minus 1 over n, negative 1 to the power of n, as well as minus 1 over n times negative 1 to the power of n, but times 3. So this comes to minus 4 over n, negative 1 to the power of n. And another way of writing this would be taking out the 4 and over n, and we get 4 over n pi times 1 minus negative 1 to the power of n. Again, I've tidied this up a bit. So if we simplify this further, we've got those 2 different cases. And we've got 2 different cases because we've got n sitting in the exponent up there. We've got things that happen if n is even, and things that happen if n is odd. So let's write this down. If n is even, what do we get? Well, if n is even, well, we've got this bit here, which becomes positive 1, and of course then we've got 1 minus 1, and that becomes 0, so the whole lot becomes 0. So for any n even, Bn is equal to 0. That means that Bt is equal to 0, B4 is equal to 0, B6 is equal to 0, and so on. Now if n is odd, we've got Bn equal to, well, let's have a look. If n is odd, then this thing becomes negative 1. So what we have is 1 minus minus 1, which is 1 plus 1, which is 2. So this is then always 2. Multiplied by 4 gives us 8 over n pi. So this is the formula if n is odd. So that means that B1 is going to be 8 over pi, B3 is going to be 8 over 3 pi, B5 is 8 over 5 pi, and so on. Okay, now let's have a look at the Fourier series, which is, the definition is listed again down there. So this all means that f of t is going to be written as, well, a naught is going to be 2, or was 2 rather. 2 divided by 2 is 1. Plus, what have we got? What is, well, the a's, a1, 2, an is equal to 0, so they all disappear, meaning we don't actually have this cost term at all. But the bn's are not necessarily all 0. So let's have a look. B1 was 8 over pi. Then we need the sine, well, n is 1, so we need the sine t. The B2 is 0. B3 is 8 over 3 pi, and that comes with a sine 3t. B4 is 0. B5 is 8 over 5 pi, and we get sine 5t, and so on. So you can see that all the an terms are 0, so the cost terms have disappeared. And half of the bn terms are 0. Now, another way of writing this, if you wanted to keep the sigma notation, and you might want to look at this just later on to see if this makes sense, we could write this as 1 plus 8 over pi. And then we write this as the series using an index m from 0 to infinity. But in here we use sine 2m plus 1 t, and we divide by 2m plus 1. And this caters for us using only the odd values of the original n. Have a think about this, but what we're after for a question like this is something like that.